Now we are moving into a concept called bidirectional diode sampling gate, which is a expert talk and detailed in explanation in our Fairytech channel. Let us go into the channel without wasting any time.
Directional diode sampling gate is constructed as shown in figure. So this requires two control signal voltages which are actually complementary to each other. See this control signal which is connected at D1. So if this is at plus Vc, then the control signal connected to D2, this will be at minus Vc. So these two control voltages are of equal magnitude, but in opposite polarity they will be applied to the diodes. So this Vs is the control signal, Vs is the input signal applied to the sampling gate, V0 is the output voltage taking from the sampling gate. Now, so let us discuss what happens. So when this control signal applying at a diode D1, if this is at plus Vc, so when Vc applied at D1 is plus Vc and Vc applied at D2, since this is plus Vc, this will be minus Vc are applied to diode D2. So what happens, these two diodes, are forward biased, means these can be replaced with a short circuit. When these two are short circuit, so then the output will be directly proportional to the input signal. V0 will be Vs as these are short circuited. Now in this concept let us discuss if the input signal is not applied, if Vs equals to 0 in this case. So then what happens, if Vs equal to 0, these two are short circuited and the voltage applied at point B, see the node P is connected with point A as well as point B. The voltage at point A will be plus Vc and the voltage control voltage at point B will be minus Vc. So as these two signals are getting connected at the node P, so using superposition theorem, this becomes plus Vc plus minus Vc. These two are equal magnitude but are in opposite direction. So the net effective voltage what you get here is 0 volts. So the output voltage will be 0 volts if the input signal applied at this gate is 0. So in this we are going to find 0 pedestal also. So there will be no pedestal here since the voltages are exactly equal and opposite. So these two gets 0. The effective voltage at node P will be 0. So this is called a transmission period at which the input signal will be transmitted to the output signal in both the directions, either positive value or a negative value. So let us see what happens if the control signal at diode D1, if this is at minus Vn, so this is at minus Vn and this is at plus Vn. What happens, so this negative voltage will make a diode D1 reverse biased, means this will be open circuited, and this positive voltage are connected at a negative terminal of the diode. This also makes this diode reverse bias, means these two becomes open circuited, and at that instance since these two are open circuited, if there will be no current flowing through the resistor as the voltage appearing across this node is 0, so the output will be 0. So the diodes D1 and D2 will be reverse biased, the output equal to 0 independent of Vs, whatever might be the value of Vs you give. If the control voltage is available at a diode D1 and D2 are minus Vn and plus Vn, so the output will be 0. So this is non-transmission period. During this, no signal will be transmitted from input to the output signal. So in this, so we need to calculate. So now how much signal is getting transmitted from input to the output, that is, so gain represent the output voltage by input voltage V0 by Vs. So we need to calculate how much input signal is transmitted to the output, and during transmission period when diodes D1 and D2 are forward biased, so we are going to apply some control signal voltage Vc. So what should be the minimum value of this control signal Vc to keep these two diodes forward biased? Means what must be the value of a Vc minimum to be applied at a diode D1? Means when Vc minimum is applied at the diode D1, then it will be minus Vc. So these two are complement. The minimum voltage applied at a D1 to keep both the diodes forward biased. And lastly, we will find during non-transmission period, means when the diodes control signal voltages are at plus Vn and minus Vn, what should be the minimum value of this Vn to keep these two diodes D1 and D2 reverse biased? So what must be the value of Vn to be applied at D2 to keep both the diodes reverse biased? So these are the things to be calculated. Why? Because if this satisfies, then only it is a bidirectional sampling gate. It acts like a bidirectional sampling gate. Now let us see how to calculate these parameters. See how the equivalent circuit, the circuit is redrawn in this figure. So if you observe, we are having four nodes here, node A, node B, and these two, node P and the input signal node. So these nodes in the circuit, so the output voltage is taken from this node. So the diodes D1's negative terminal is connected to node P and D2's positive terminal is connected to node P. So D1's negative terminal is connected at node P, D2's positive terminal is connected to node P. From node P, we are having a load resistance RL here. RL is placed like that. And coming to these nodes, the input signal is connected to R2 resistance from D1 and R2 resistance from D2. So the D1's positive terminal is connected to R2. So D1's positive terminal is connected to R2, and to R2 we are connecting this input signal Vs from this. And similarly D2's, so D2's negative terminal is connected to R2 and R2 is connected to Vs. So D2's negative terminal is connected to R2 and it is connected to input signal Vs. So the input signal is applied at this node. This node is replaced here and this node P is available here. Now coming to control signal voltages, here see from D1's positive terminal, so we are forming node A here. So node A is connected to RC to control voltage. So from D1's positive and resistance R2. So from D1's positive and this resistance R2 we are having a node A. A is connected to RC to control voltage Vc and to the ground as it is, as shown here. Similarly, considering node B, it is available between diodes D2 negative terminal and resistance R2. So diodes D2 negative terminal and resistance R2. So in between we are having a node B. Node B is connected to RC and we are having control signal minus plus. This is a complement to each other, since these control signal voltages are having minus and plus Vc towards the ground. So this is how this circuit is redrawn into this fashion. So to find out this gain of the circuit, we have to reduce this circuit using a Thevenins equivalent. So how to reduce? Let us see. So in this circuit, so if you want to replace if you want to identify output by input, so let us replace this circuit with the help of Thevenins equivalent as shown in figure here. Let us say the same circuit, we need to identify what is the resistance, Thevenins resistance looking out of this input signal, means from this out to the input side and from this to the output side. So from this circuit we are having two voltage sources here. To find out VTH, so we use a superposition theorem. We will consider one voltage at a time and then we will find what is the Thevenin's voltage, and to find Thevenin's resistance we will short these voltage sources and we will find. So since the two stages are identical, diode D1, RC and RC, these terms are identical. Now let us calculate what is VTH from this from input side. So this is RL. Now so VTH, let us take first this control signal as 0. Consider only this voltage. Now what happens in this point, so the voltage, the circuit appears like this. A voltage source Vs is applied, the voltage signal is applied across a resistor R2 and a resistor RC towards the ground, and the voltage at node A is to be noted. So what happens to this, so VA can be calculated as, VA is the voltage when signal source is considered here. VA equals to what happens, so RC by R2 plus RC into Vs. So this is a Thevenin's voltage for by considering Vs signal. So by replacing this ratio RC by R2 plus RC as a alpha, then VA equals to alpha Vs. So this is one voltage. So now coming to other one, so by now let us consider only VC voltage and make Vs as 0, means a short circuited. In this point we see now, so the voltage at node A, so here this VC signal, this source VC is, the circuit is like this, connected through two resistors RC and R2. So and the node voltage is across this is VA. Now so this voltage is VC, can be calculated using a voltage divider formula itself. It becomes so VC into R2 by RC plus R2. So this is, so the voltage, Thevenin's voltage, by making this Vs equal to 0. So when we replace this RC by R2 plus RC as alpha, then this is can be written as 1 minus alpha into Vc. So where alpha equals to RC by R2 plus RC. So these are the Thevenin's voltages available at this stage, at this point. Now to calculate effective resistance, so let's make all the voltage sources available as 0, so means by short circuiting. Now what happens to the resistances available here, we are having a resistance RC to the ground, and we are having a resistance R2 again to the ground. So the total resistance what we are having is here RTH equals to, so RC parallel with R2. So this is the Thevenin's resistance available for this one. So by replacing all these, so since the two stages are identical at the output side as well as at the input side, so on both the sides, so we'll have the same. Here the circuit is replaced with RTH, and here we are having two voltage sources. So this is alpha into Vs, and this one is 1 minus alpha into Vc. So this is plus minus and plus minus. So here also we will have RTH, and here also we will have two Thevenin's voltage sources like this. This is alpha Vs plus minus, and this is 1 minus alpha into Vc. This is minus plus, since these two are complementary control signal voltages. Now this is the Thevenin's equivalent circuit. And again, to further simplify, if we replace this diode into its piecewise linear characteristics, means the diode is actually the diode can be indicated in terms of a series combination of a resistance, which is RF, forward biased resistance, with a threshold voltage of V gamma. This is the piecewise linear representation of a diode. If we replace this D1 and D2 in this form, so then the circuit again gets simplified. So this is the Thevenin's equivalent circuit for this. Now, so by replacing the diode, now taking this RTH, considering this RTH as R1 now. Consider this RTH as R1. So where R1 equals to RC parallel with R2. Now the diode is replaced with its RF as well as V gamma and RF. Now what happens, these resistances R1 and RF are in series, so this may form a series resistance. Let us consider it as a R3. Similarly R1 and RF here as R3. Now so where alpha equals, see, R1 equals to R2 parallel with RC, and R3 equals to R1 plus RF, and alpha equals to RC by R2 plus RC. Excuse me. Now further reducing this in with its Thevenin's equivalent, let us say I wanted a Thevenin's equivalent in this form. This is RL, which is V0. So I need a Thevenin's resistance RTH and a Thevenin's voltage Vs. Now the Thevenin's equivalent across a load resistance RL. So I am taking this one as RTH and this one as VTH. Now the Thevenin's equivalent voltage VTH can be directly written or simply identified as VTH equals to alpha Vs. So since this control signal is having no effect on the circuit, as well as this gamma, these two are parallel and these are complementary, and this doesn't have any effect on this. So at any instant of time, the voltage what we find across this load resistance is alpha into Vs. So VTH equals to alpha into Vs. Now coming to RTH, Thevenin's equivalent resistance. So when at this node P, the Thevenin's equivalent, the complete branch So this entire branch, and this branch from this side, these two are in parallel, means both R3 resistances will be in parallel with each other to find RTH. So then RTH will be R3 parallel with R3, that is nothing but RTH equals to R3 by 2. So by reducing this one using a Thevenins equivalent circuit across the RL terminal, the circuit be finally reduced in this. The circuit will be reduced in this form. So this is the final Thevenins equivalent circuit, from which we can easily find what is the gain, the voltage across this load resistance V0. So V0 equals to, using current division rule, using voltage divider rule, we will find alpha Vs into RL by RL plus R3 by 2. So V0 by Vs equals to alpha into RL by RL plus R3 by 2. So where alpha equal to RC by R2 plus RC. So this is gain of this circuit. Let us calculate what is the minimum value of control signal voltage required to keep both the diodes forward bias. Let us see how the minimum value of Vc can be calculated to keep both the diodes in forward bias and to make this circuit work as a bidirectional sampling gate. So see here, let us say, so when these Vc, both the signals are given, both the diodes are forward biased, then input signal of, let us say, input signal of 2 volts. 2 volts is applied across this. What happens, as this one, as the input voltage here is, this diode is forward biased, what happens, this voltage, it becomes more forward biased. Diode D1 becomes more forward biased, and diode D2, since we are applying this, so positive voltage to the negative terminal, here the diode gets lesser forward bias. It reduces its forward biased condition. So this one, as the input signal goes more positive, diode D1 will be more forward biased, and the forward bias of diode D2 will be decreasing. So we have to stop a condition at that. So when diode D1 is forward bias, and diode D2 is just entering into a reverse bias, not complete reverse bias, just entering into the reverse bias, diode D2. At that condition, if we find the voltage, when the output voltage when diode D1 is in forward bias, and the voltage output voltage when diode D2 is in just entered reverse bias, and equating these two means V0 at D1 forward bias equals to output voltage V0 at D2 just entering into reverse bias condition, and equating these two will find the relation for Vc minimum. So let us see, let us find the output voltages based on that conditions. So as we said that, so this diode D1 should be in forward bias, and diode D2 just entered into reverse bias. At that time we need to find the output voltages. See, considering this loop forward bias condition, since this diode is forward bias, current flows through these resistances R1, R3 and RL. So the entire voltage falls in across these drops across these resistances R3 and RL. So writing the relation, we will get V0 equals to alpha Vs plus 1 minus alpha Vc into RL by RL plus R3. From this slide, like this, voltage is RL by opposite resistance voltage by So total resistance RL plus R3. Now coming to the right hand side, since this is a open circuit, reverse bias, just entered reverse bias, we don't find any current flowing through these resistances. The entire voltage whatever available here, that will be obtained at the output terminal. V0 equals to alpha Vs minus of 1 minus alpha into Vc. So equating these two, we will get to a relation by solving this equation into Vc minimum equals to Rc by R2 into R3 by R3 plus 2RL into Vs. So this is the minimum control voltage to be applied to ensure that both the diodes are in forward biased and the circuit acts like a bidirectional sampling gate. So to be remembered, a point here is that this D2 is not completely reverse biased. So this one was more forward biased and this has just entered into reverse bias condition. At that instant we find out this Vc minimum value as shown here. Now let's find what is the value of minimum positive voltage of Vn here. Now this Vn is applied during non-transmission region, means when both the diodes are in reverse biased condition. So what is the value of a minimum Vn which keeps both the diodes reverse biased? Now consider this here, when both the diodes are reverse biased, so the circuit should be actually like this. So diode D1 reverse biased, this is load resistance RL, and here also diode D2 reverse biased, and here also we are having the voltage sources. Now in this, so one thing to be remembered is we are considering only that loop where we are applying a positive value for Vn. So we consider only this loop. Why? Because this is plus alpha Vc and here the value what we have applied is a positive Vn. So 1 minus alpha into, so Vn plus Vn we consider, considering only this is second loop. Now since the diode D2 is reverse, D1 and D2 are reverse biased, now what happens here? So what is the worst case situation what we get in this is, see, taking a loop here we'll get, so taking plus minus, this is a diode voltage Vd, so Vd equals to Vd equals to minus alpha Vs, so plus 1 minus alpha into, so Vn what we get. So by considering the worst case, so both the diodes to be reverse bias, what is the worst case? That some diode may enter into a forward bias. So the worst case for this diode not to enter into forward bias is, so this Vd should be 0. So this is the verge, means edge of the value at which the diode may enter into a conduction state, forward bias state. So up to this, so this is the worst case value here. Taking this, so and by writing this loop equation, so we'll get a value called, so by at this instant Vd is 0, substituting that Vd equal to 0, so we get alpha Vs minus 1 minus alpha Vn, 1 minus alpha Vn equal to 0. So from this we can find Vn equals to alpha by 1 minus alpha into Vs. So this is the minimum value of control voltage Vn to ensure that both the diodes are in reverse biased condition and the circuit works as a bidirectional sampling gate. So let us discuss some disadvantages of these two diode sampling gates. So the disadvantages are listed here. So the gain of this two diode sampling gate is quite low, and since we are having two control signal voltages here, so this one is very sensitive to the control voltage imbalances. If one value is plus Vc and if the other value is not exactly minus Vc, then we may expect a pedestal at the output side, so which is not actually desired. So it is very sensitive to the control voltage imbalances, and there is no possibility that Vn minimum may be excessive here. And the last one is there may be a appreciable leakage through the diode capacitance. Now all these drawbacks in 2 diode sampling gate can be improved with the help of 4 diode sampling gate, which we will discuss in the next class. So thank you for listening to me. Meet you in the next class.